Recording again. I put this photo in the chat window as well, but um, I forgot to get my rocks um, to bring them before class started, so I went and got them during the break. And this is a good example of two felsic rocks that have, if not identical, probably really, really similar mineral composition. And the reason this is all uniform in color is because, once again, the grains for the most part are too small to see, so they all bleed together. All these different colors bleed together into one generally light pink color. We'll learn Thursday what that mineral is that's given us the pink um, color, but you got intrusive phaneritic granite on the left, and you've got extrusive aphanitic rhyolite on the right. I just added this slide, so it's not on the slideshow that is posted on Canvas, but I will make sure that that a new version will get posted sometime today. And I don't know why I have a that's not blank. That's got our outline. Before we talk about our three types of volcanoes. And when I say our three, some textbooks talk about four. Um, I consider that I consider that fourth one a minor type of volcano, so we're not going to get into that. Um, but before we get into those three, let's talk about just what a volcano is. And I ask y'all to come in on the chat here. And when I say volcano, when I say the word volcano, what's the first thing that pops to mind? What do you get a mental picture of in your head? Okay, some of us get lava, magma, cone shape, a mountain. Um, and for me, when someone says volcano, I immediately picture a mountain. I immediately think of a conical mountain in my head. When someone says volcano, I'm thinking of a mountain because that's first off what a volcano is. A volcano is a mountain. Question is, why is it a mountain? Some misconceptions that perhaps it is uplifted because of the magma underneath is causing the earth to bulge. That is not the case. A volcano is really just a big pile of extrusive material. Stuff comes out of a hole in the ground, and that stuff winds up being piled up. It winds up cooling into rock close to the vent. So if you keep piling stuff close to where it comes out, then you're eventually going to get a conical landform. So volcanoes literally are just piles of extrusive material. They are piles of extrusive material. Um, Now, some of the parts of a volcano, the vent is the hole that molten rock comes out of. It's a hole in the ground. Maybe it's a tiny crack, maybe it's a big hole, but it is the hole through which the molten rock comes. Crater is not the hole. Crater is a depression above the vent. A crater is a depression above the vent. Um, so they are closely associated, but they are not the same thing. Um, Not all vents are at the summit of a volcano. Flank eruptions are not uncommon. Even eruptions from the base could be present. Uh, and then, of course, the conduit through which the magma comes to the surface, somewhere down here, is going to be a big magma chamber. But this conduit is called a pipe. So we want to make sure that we are familiar with those, um, with that bit of terminology. And now I've got another term that's not in this photo, and we see in the foreground of this photo is a pretty obvious crater. Right here, we're almost at the lip of this crater. Somewhere down in here, it's obscured by that edge, but somewhere down in there, you have a vent. But this crater is the depression above the vent. In the background, we have another feature that kind of resembles a crater. It is it is a depression. It's sloped in on all sides towards the water, but it is much bigger than this crater. So that's one thing that that's kind of a vote against that being a crater. But this is a volcanic landform. What this landform is, and I'm going to go back to this one. Show. Let's imagine that we have a really big magma chamber below this volcano. And of course, before the eruption, that magma chamber is full of molten rock, which helps to support all this heavy material here. But during an eruption, and especially explosive eruptions, because explosive eruptions tend to get their stuff out pretty quickly. During and just after an eruption, you might have a big emptiness down here, as most of the material in that magma chamber is erupted into the atmosphere. Then you have what was once full of material is now a void space. It's a big hole there that does not have a lot of support for this overlying mountain. And so what frequently happens is the mountain will collapse into that emptied magma chamber. It will collapse into that void and lose several hundred feet of its height. The mountain, it will look like it blew its top, but in reality, what happened is the top collapsed down into here. The whole thing collapsed. This part collapsed down into there as well. And so what you're seeing in the background there is a collapse structure. It's not a crater, but it is what was once a much larger volcano like this. And most of that volcano is gone now because it collapsed into this void there. That collapse structure is called a caldera. And a caldera is usually a sign that there has been a large explosive eruption. So there's the last bit of terminology. Calderas are frequently filled with water. They don't have to be, but they frequently are. So here's the three types of volcanoes that we want to be familiar with. Now, this is in your textbook, except your version of the textbook has eliminated what I feel like is a really important part of this figure. So I'm going to grab the page number for this real quick. I'm in the wrong chapter. Let's get to 4, why don't we? So page number for this is, watch it not be in there. It is page 92. It's still table 4.2, but it's page 92. The thing you will find on page 92 is that this bottom part is missing. This bottom part here is drawn, and I consider that kind of essential. That's essential because what it did with this bottom part was it drew all three types of volcanoes, shield, composite, cinder, at the same scale. These are drawn to the same scale. Whereas these three are drawn at different scales. But students who just take a glance at that, anyone who just takes a glance at that, may not pay a lot of attention to this scale on the left. They may not generally pay attention to that, and they'll just say, oh, cinder cone composite, about the same size, composite a little bit bigger, shield is really short, but it's a little bit broader than the others. When in fact, a shield volcano dwarfs the other two. It dwarfs the other two both in height and in width. It is a gigantic landform. So this is better because it shows all three drawn to the same scale. Now, admittedly, this has a scale, but we don't always pay attention to those things. So let's talk about the shield volcano first. As we said, it's the biggest volcanic landform. It's the biggest volcano, but it doesn't really look like a volcano. It doesn't really look like a volcano. It's gently sloping. It's not a cone. It's not the traditional conical volcanic landform. Its slopes, as you see in that table, are 2 to 10 degrees. That's a gently sloping landform. Generally, people who aren't familiar with them don't glance at a shield volcano and say, oh, that's clearly obviously a volcano. So the question is, what we would like to be able to do is tell why are these volcanoes slope so gently? And let me emphasize, because I may not have emphasized it enough, that these are the tallest volcanoes. They are much higher in altitude from bottom to top than the other types. They just don't always seem like they are because they're so gently sloping. But slope is not the same thing as elevation. Slope is change in elevation per distance. So these things might be 13,000, might be 17,000 feet above sea level, but still be really, really gentle. So they are gentle. What are they made of? They're made of mostly basalt, just lava flow after lava flow after lava flow of basaltic lava piling up. Usually started, not always, but usually started at the seafloor. So basaltic mafic lava coming out of a vent in the seafloor and eventually building up so thick, literally thousands of lava flows building up so thick that it breaks sea level and then might build up thousands of feet above sea level. So you've heard some people say that not Mauna Loa, but Mauna Kea on the Big Island of Hawaii is the largest mountain in the world if you count from where it begins at the seafloor, because it's actually there's actually more of it below the waves than there are above the waves. Anyway, basalt, you remember, is mafic. Mafic is runny lava. Mafic is runny lava, and that means that it can travel because runny lava is faster than thick, gooey lava. Then it can travel a lot farther from the vent before it cools. That means that these lava flows will travel a long way from the vent before they cool, which means not as much piles up right around the vent. This is why they have such a gently sloping, why they have such gentle slopes, is because the lava, being mafic and low viscosity, travels a long way from the vent. Um, it's not uncommon for the lava to make it all the way to the ocean from there, several kilometers away. We're going to see a photo in a little bit of a lava tube. So sometimes the lava flow, the top of it can crust over, but below that's still insulated and still flowing. That can make it flow even farther than it normally would. So, eh. So the person who shot this was standing near the summit of a shield volcano, and we see how gently sloping it is. In the background is a second shield volcano, also really gently sloping, definitely not conical. Want to also notice the dark color of the rocks, which is what we would expect with mafic magmas cooling into basalt. You might say they're not all dark. That's a pretty light colored brown. Well, Hawaii is a really humid climate, and volcanic rocks start to weather pretty quickly, and there's a lot of iron in basalt, and it weathers to iron oxide, so you get brown. Volcanic rocks turn brown pretty quickly due to the iron in them oxidizing. Um, what else do we have? Here's I'm not sure how much I like this, but we'll let it go ahead and cycle through its deal. Building of a shield volcano. The main thing to notice is that it's all lava flows. Yeah, sure, there's a little bit of cinder activity going on here, but it's mostly just flow after flow. And notice how broad but gently sloped it is. Here's another shield volcano. I'm not 100% certain this is Hawaii. It could be the Galapagos Islands. They are also shield volcanoes. Iceland is shield volcanoes. But again, notice how dark the rocks are. That means fairly fresh volcanic rock. And notice how gently sloping it is. Again, this does not put many people into mind of shield volcano. I mean, I'm sorry, of a volcano. So again, because these are mostly lava flows and low viscosity, shield volcanoes usually erupt in an effusive manner, a non-explosive effusive manner. In the background are two more shields, and those are very likely the same ones as we saw here. It's just that we're standing on one of them there, but I can't be certain. But we have two gently sloping shields, and this is shot from another island looking across the ocean at those. But these things in the foreground are not shields. They're way too small. They're both too small in width, they're too small in height, and they're too steep. So these are not shield volcanoes. Here's a lava tube that has crusted over. I'm sorry, here's a lava flow that is crusted over, forming a tube. So the lava below there is still flowing, even though the top has dried. So remember, I said you got to be that lava is not going to kill you. Well, if you walk on this crust before it's formed too thick, then it will collapse. Generally, they don't let you do that. The second type of volcano we see here, we see first off, obviously, it is steeper than a shield volcano. It has the classic volcano shape, and it is smaller than a shield. It's not nearly as tall from bottom to top, and it's not nearly as wide around. Excuse me. A cinder cone, it's the second type. A cinder cone, by definition, mainly spews out it spews out lava that's really gassy, forming these vesicular cinders, the lava rocks that are found at Lowe's and in people's gas grills and in landscaping at Taco Bell. It spews out those things. So it's what you would call minorly explosive. A much larger explosion um, would create ash, but these are creating cinders that fall really close to the vent. Also, just now saw a face in there. We always see these devil faces in the volcano. So what about a cinder cone? Steepest of the three, also smallest of the three. Cinder cones are small. They're usually not more than a few meters tall. They do not last very long as a volcano. They might erupt for a 10-year period or a 1-year period or a 30-year period, and then they're usually pretty much done. They can also form on the slopes of a shield volcano or the slopes of a cinder of a composite volcano, or even in the caldera of a shield volcano, which we saw a bit earlier. These ones here were 3 cinder cones inside a shield volcano. So what are they made of? Still basalt. Notice that shield volcanoes and cinder cones are both mostly basalt. Same composition of stuff, which means the magma should be low viscosity. But these things look so different. Why do they look so different? Because a cinder cone is usually just a local high gas concentration. Remember that all lavas have gas in them, but some have a lot more than others. So when there is a local concentration of gas, then you might get the stuff coming out as cinders and forming a steep landform as opposed to just flowing out. So again, same composition, but here it flows out effusively, and here it comes out as these cinders, which we're fixing to see in a second. With some time-lapse nighttime photography, we can see the path that most of these glowing means they're still somewhat molten as they're coming out of the vent. We can see the path that most of them are taking, and they're falling real close to the vent. Hey, if you keep piling up stuff close to the vent, you're going to get a steep landform. If you pile stuff a long way from the vent, you're going to get a gentle landform. So cinder cones are steep, and they usually really are just a loose pile of those cinders. I've hiked in one before, and it's not a pleasant experience because you sink down so much in those loose cinders. And when you get on steep ground, you stick your foot in and you slide backwards in it. It's really, really loose. So the thing that we maybe want to get from this little thing I stole off the web, if it's actually going to even play, is it's not going to play. I bet it will play on the one that we have posted, but the thing that we want to get from it is that it is much steeper than the shield. And you see that instead of lava flows coming out this way, you're seeing a lot of the cinders fall. However, a problem with this is, once again, they're showing it at different scales so that it looks as big as a shield when it is not. Here is a classic cinder cone out on an island off of Iceland, showing the steepness. Also, it's not overall gigantic, and the material is, even though it's going way up into the sky, it's still falling fairly close to the vent. making a steep landform. So we saw that those were cinder cones earlier as well. The third type of volcano are composite volcanoes. You might also see them called stratovolcanoes. There's at least three in this photo. You've got the one in the background, you got the one in the foreground here, and then there's another one behind it that it's partially obscuring, which when I try to draw, sometimes I get all these horizontal lines. I don't know how to get rid of them, but anyway, there's a third volcano back there. As you can see, composite volcanoes are large. We're going to compare them to the cinder cone size in a little bit, but they also have the classic shape. They have the classic volcano shape. So people that see a composite volcano, they immediately are like, yeah, that's a volcano. The word composite simply comes from the fact that sometimes a composite volcano is going to erupt lava and sometimes it's going to erupt ash. So it's made up of alternating layers of ash and lava. Composite volcanoes can grow really, really high. This is one in Mexico called El Popo, and it is about 18,000 feet above sea level. Some of these, many of these, I should say, are so high that they have year-round snow cap on them. This is important in Chapter 9 when we get to forming lahars as a result of eruptions. But many, many of them are snow-capped. Composite volcanoes produce ashfall, pyroclastic flow, and lahar. Almost every time they erupt, they will produce all three of those. So of the three types, these are by far the most hazardous of the volcanoes. They're the famous volcanoes. If you've heard of a volcano that is famous for whatever reason, it's likely because it was destructive or deadly. Mount St. Helens is a composite volcano. Let's look at the graphics here. So 1 to 4,000 meters, which means like 3,000 to 13,000 feet high. So these can be really big. Compare them to a cinder cone. They will dwarf cinder cones, but they are in turn dwarfed by shield volcanoes. So you might say that they're kind of in between, but they're still, if you stand on the slopes of a composite volcano, you will get the feeling of this being a really large landform. Why do these erupt so explosively? The answer is right here. The material that comes out of them is mostly intermediate in composition. Remember that intermediate, if we go way back on that chart, we see that intermediate still has high viscosity. So when this thing erupts lava, the lava is thicker. It's thicker than this lava here, which means that it's moving more slowly and more likely to cool close to the vent. And when it's not erupting lava, when it's erupting explosively, then you're going to get a lot of ash fall close to the vent, because ash, even though it's really, really light, it also contains weight. Also, when those pyroclastic flows, if that ash cloud collapses, we get pyroclastic flows. That stuff is deposited right here on the slopes of the things. So these are steeper. These are the famous deadly volcanoes. If you think of a volcano that you've heard of, it's probably because it is a deadly composite volcano. Mount Fuji is a composite volcano. Mount Ararat, Mount Vesuvius, Mount St. Helens, Mount Hood, Mount Rainier. If you can think of any more that have been really, really hazardous and destructive and deadly, chances are they are composite volcanoes. Let's keep this andesite thing in mind, because we're going to come back to that in a second. Oh boy, this one's going to work. And what it's doing is showing alternating. There's some pyroclastic flows in ash cloud, then there's lava. Then pyroclastic flows in ash fall, and then lava. So yes, it is going to be steeper than a shield. Excuse me. It makes me want to try that cinder again, but the cinder's probably the worst of the three, so I don't really care about it. Okay, there's Mount Rainier. We see just how much snow is on there. That's a serious amount of snow, even glaciers on Mount Rainier. Mount Rainier is a composite volcano. Crater Lake in Oregon is a composite volcano. Now, when we look at the size of this thing and the steep cliffs all around that lake, it may make us think for a second that is that really a crater? Because in fact, this is not a crater. This is a caldera. So if you were going to be pointy headed about it, they should have called Crater Lake Caldera Lake. It should have been named Caldera Lake, technically. But it's not. Maybe it wouldn't have been as attractive. It's called Caldera Lake. Now, there is a crater in this photo. It's on this thing right here. This is a little cinder cone because, as frequently happens when a composite volcano collapses into a caldera, that doesn't mean the volcano is done erupting. It will start sometimes that day, continue to erupt stuff, and it may start building up composite material or cinder cone material in there. And that's exactly what has happened here. Is sometime in prehistory, in prehistoric times, when this collapse happened, sometime after that, you had some more rejuvenated activity building up a cinder cone in there. And in the background, we see another volcano, another composite volcano. These are part of the Cascade Range, which are chains of volcanoes, somewhat linear chains of volcanoes. We'll see why that is in a second as well. This is Mount Rainier again. I was fortunate enough to take that from an airplane. This is Mount Adams taken from the lower slopes of Mount St. Helens. And then this is Mount St. Helens taken from the slopes of Mount Adams. So I took that picture, but I didn't take that one. I might have a bit of money if I had taken that one. It's a fairly famous picture. In 2006, we were fortunate enough to get hiking passes. They were giving out 100 a day, I think, and to allow us to hike to the top of St. Helens. As you can see, there's a whole wall of St. Helens caldera or crater missing, because when St. Helens erupted, the north face slid off of the front of that mountain, and it had so much momentum, all that material actually went over the next ridge and into the next valley. And that was like taking the cork off of a shook up drink, because all that weight left behind and all the gases in there just immediately flashed to steam and blew out both upward but sideways. So we can see there was an upward blast, but there's also a lateral blast. People who were in this zone did not fare very well for St. Helens. This Spirit Lake near St. Helens, this is a raft of trees that was blown down in 1980, and about 2/3 of them have sunk, I believe, and there's still about 1/3 of them left that just float around depending on which direction the wind's blowing. They may, one day they might be over here and the next day they might be over here. Bottom of that lake is just covered with timber that was blown down, because this is the Pacific Northwest. It's a humid area, and it's heavily timbered, or was before 1980. This is a seismograph on the slopes of Mount St. Helens, because one of the best ways to know that an eruption is imminent is when the magma starts moving closer to the surface. It shoves rock out of the way and cracks rock, and that creates tremors. These tremors have a different signature on the seismograph than do regular tectonic earthquakes. So the mountain is surrounded. For that matter, Yellowstone, the supervolcano, most of our active volcanoes in the U.S. are surrounded by seismographs. So the picture that I took of looking off into the looking to the north where the face was gone, that was taken probably right around, it was taken somewhere on a fairly low point on the crater. They didn't let us go over here. They didn't let us go down into there. So this is taken from the north looking south, and you can see not only that the whole north wall is gone, but also this was a conical mountain before that collapse. So yes, there is a caldera now, and this thing right here is renewed growth. So will St. Helens ever be a perfect perfect conical mountain again. Someday it probably will be. Not all composite volcanoes are along the Pacific Rim in Indonesia, but the great majority of the world's composite volcanoes are. They form linear chains, and if you can think back to last week, you probably have figured out why now. We're going to go back some slides and look at the composition of this. Remember, they're explosive because it's really viscous lava. It is intermediate andesite. So where does that andesite come from? It's not going to form just anywhere. Andesite is not going to form on mid-ocean ridges such as here or the mid-Atlantic ridge there, because those are divergent boundaries which lead to decompression melting, so that the upper mantle, the ultramafic material, partially melts into mafic magma. So we got our ocean floors made of basalt. But all along the Pacific Rim, you got this oceanic crust, which is mafic. It is being subducted below the continents. It's being subducted below South America and below Central and North America and Alaska and Russia and Japan. Oops, that was Japan. And Philippines and Indonesia and even some in the Mediterranean there. There's subduction. So what we have is an oceanic slab going below the continent. Here we go, basalt. Basalt is an oceanic slab, and this will be the thick continent. Remember, that oceanic slab is bringing water with it. Excuse me. And when that water encounters the mantle, then introducing water lowers the melting point. So once again, we have ultramafic material in the mantle, which is going to partially melt. With the addition of water, it's going to partially melt into mafic magma. But this mafic material, on its way to the surface, as it melts, it has to pass through all this felsic stuff. Remember from last week that the continents are mostly made of granite. So when you mix mafic stuff with felsic, you're going to get intermediate. So all along these areas, right about where the zone of melting is, you go directly above that and you get a chain of volcanoes on the edge of the continents. And these volcanoes are predominantly andesite. Or you get a chain of volcanic islands off of the continent, but still they tend to be linear because that slab is bringing water in, and so the mantle is melting all at about the same depth, which gives you a chain of these volcanoes. Plate tectonics explains this really, really well. How come the volcanism in the middle of the oceans is generally mafic and effusive, but the volcanism along the Pacific Rim and Indonesia is explosive? Plate tectonics does a great job at that. Not all volcanism leads to a volcanic landform. Not all extrusion of molten rock forms a cone. Two exceptions to this are lava floods and pillow basalt. And I believe the name lava floods is one that your textbook used to use, and they've decided to not use that one anymore. And so I think they're calling them flood basalts. Oh, there it is. It's on the slide. I think your textbook has switched over from this term to that term. Any geologist would know what you're talking about if you used either one, but this is what the book is using: flood basalts. Flood basalts are basalts that come likely from a hot spot as the crust moves over a hot spot, leading to melting. But the magma, the molten rock there, has such low viscosity that virtually none of it cools off at the vent. Instead, this lava, and we're talking about huge volumes of the stuff, this lava extends and fills up all of the low areas, all the stream valleys and other low areas, and then starts filling up those areas and may even begin to cover some of the high areas. Voluminous amounts of lava flows. There are extensive flood basalts in Washington and Oregon, in the US, as you can see right here. But these are common both on land and in the ocean. There have been extensive ones of these. And in fact, excuse me, the stuff here is now has now been blamed for the Permian extinction, the extinction at the end of the Paleozoic before Triassic that resulted in extinction of about 95% of the landform. I'm sorry, of the not landforms, of the life forms at the time. That's a good question. I think that under the ocean, there are active flood basalts, but I don't think we have any on land right now. I think the closest we come, and I don't think you would consider it, but the closest we come is Kilauea on Hawaii or Iceland, and I don't think they qualify. In 1783, I'll get to that one in a second. 1783, one of the volcanoes on Iceland had such a had about a 9-month eruption and put so much material into the air that was then precipitated to the ground that it poisoned livestock. So much fluorine and selenium and other things poisoned the livestock, and it led to a famine then. That is sort of like a small version of a flood basalt. So I shouldn't say we don't have any now, because 1783 and geologic time is still pretty recent. None of this magnitude, though. This put out so much gas that it's believed to have changed the ocean chemistry at the time. So much CO2 acidified the oceans so that it wiped out most of the ocean creatures at the time. Not all. We still got sharks. We still got fish that made it through there, but an awful lot of them there. And now some people are arguing that the dinosaur extinction was not the result of a meteorite colliding on the Yucatan Peninsula, but was the result of these lava flood basalts there. The pillars, the columnar basalt that someone has asked about, and just in case you don't know what I'm talking about, I'm going to do a quick search for them. The columnar jointing, it's usually basalt, but others can do it. That is thought to be the result of shrinkage as it cools. It's thought to be the result of shrinkage as it cools. You'll notice that they do tend to form perpendicular to the orientation of the flow. And the joints, the pillars, actually go down all the way through there. So it's thought, the last time I had read anything about these, it wasn't conclusive, but people thought that they were the result of the shrinking during cooling. That's how the columns form. There are 3 short videos here about these flood basalts. I don't know which is which. I think in a little bit I may watch one of them, but we're not going to watch all 3. But I think they are really short, just to see those. But before we do, let's look at some more photos of these flood basalts, because they are extremely thick in the Pacific Northwest. In Washington and Oregon, they are thousands of feet thick. The eruption happened for so much lava for so long that they created thousands of feet of basalts there. This is a waterfall on the Oregon-Washington state line that's 500 feet tall, and all of that is basalt. And as you can see, this is probably more than 500 feet from top to bottom there. Okay, the second non-conical landform that occurs is when lava erupts on the ocean floor. When lava erupts below the water, it has the weight of the water to contend with. So the weight of the water, if we get pretty deep, then that water is really, really pushing down. It's really pushing down on that lava, trying to keep it from coming out. But the lava has the strength of all the heat and the pressure below it pushing out. So they're at war, and the lava does wind up pushing itself out, but it cools so quickly that a crust forms there and it has to kind of push out to the sides. Rather than me do that, this is also linked in Canvas, but let's just have a look at this one. Get to see some good footage. Pillow basalt. Reminds me of snakes on the 4th of July. Little cylinders you light, ashes come out. So instead of a conical landform, what you might have is extensive pillows of this. And so, and that I just looked at the chat and I realized that there may be some confusion. This is pillow basalt, but basalt pillars are what I described earlier. So hopefully they are two different things, but they sound a lot of. Okay, so that is what have we been watching at my house, huh? That is what the pillow lava, how it is formed. So let's see which one of these lava floods I want to look at. Probably I want to watch the short one. So let's see what this is. Okay, that's going to be short.
Hello, young people. The Columbia River basalts near Quincy, Washington. We're at Quincy, Washington, but we could pick any spot between Spokane, Washington, and Seaside, Oregon to do this show. These brown layers of basalt are everywhere in the place where the Ice Age floods did massive amounts of erosion thousands of years ago. There's more than 300 layers of basalt here, 300 separate volcanic eruptions, and the stack of basalt is more than 2 miles thick in places. The lavas started erupting 17 million years ago here and flooded a landscape, buried a landscape in lava. The obvious question is, which volcano erupted? Was it Mount Rainier? Mount St. Helens? The answer is none of those. The Cascade volcanoes do not match the chemistry of these basalt lavas. These are lavas that came from the east. They erupted out of fissures, deep cracks, that emitted Hawaiian-like lava starting 17 million years ago. Fissures that formed related to the birth of a hotspot that's now underneath Yellowstone National Park in Wyoming.
Is there going to be more? There is more.
Is the key to the past. To really visualize eastern Washington 17 million years ago, we need to go to Hawaii today. Those Hawaiian lavas today are the same kinds of lavas that we have here. Lava flows in Hawaii, very fluid. The most fluid lavas we have in nature average less than 3 feet thick. Here in eastern Washington, the lava flows average 100 feet thick. In Hawaii, the lavas travel on average 3 miles in length. Here in eastern Washington, many of the lava flows traveled 300 miles. And in Hawaii, 30 miles are covered by a typical flow. Here in eastern Washington, 30,000 square miles of area buried. The Columbia River basalts near Quincy, Washington. It's all out here to see.
It was a little more than a 2-minute geology, but that may have been the best one. That's the one I want to watch because did a great job in that small amount of time. So there's our take. Oh no, there's our takeaways from this chapter. I'm going to leave those up for a. I'm going to leave these up for a few minutes, for a few moments, not for a few minutes. And in just a little bit, I'm going to stop the recording for this, and I'm going to start a new recording, and we're going to spend 5 or 10 minutes doing a quick recheck of our minerals from Thursday. I don't have I don't have the samples with me today, so I'm just going to look at that photo and I'm going to say some words about the photo that I put up, or maybe the individual photos because they're a little bit better. So this slideshow, by the way, is posted if you need it, and I am going to post the update with that texture picture, the one that I'm so fond of right there. But let's go ahead and stop that recording.